So an indicator is a substance that we use to find where the equivalence point actually happened. So it changes color at what's called the end point of a titration, which we want to be close to the equivalence point, or else the color change doesn't actually have any meaning. So the end point of a titration is when the indicator changes color, while the equivalence point is when all the acid and base are neutralized. It's based only on the stoichiometry of these substances. Whereas, again, the endpoint is just when the indicator changes color. So they're not always exactly the same, but ideally they would be. So most indicators are just weak acids, which we represent with HIN, where H is the acidic proton and IN is just the rest of the indicator. So when it's in this form HIN, it's one color, but when the proton is lost and it's just IN minus, the indicator is another color. So that's how the color change happens. One example of a indicator is phenolphthalein. So phenolphthalein is colorless when in an acidic solution and pink in a basic solution. So when in an acidic solution, the indicator will be in this form, HIN, and in a basic solution, the indicator will be in the IN minus form, because this is the dissociation equilibrium of the weak acid indicator. And so in an acidic solution, there's a lot of extra H plus ions. So by Le Chatelier's principle, the equilibrium is shifted to the left, and this form of the indicator dominates. Whereas in a basic solution, there's a deficiency of H plus. So the equilibrium shifts to the right to produce the IN minus form. So when does this color change actually occur? And it occurs when 1/10 of the original form of the indicator is converted to the other form. So let's say we have an acidic solution being titrated with a basic solution. So the initial form of the indicator will be the HIN form. And then as we add more and more base, the equilibrium will shift to the right, and more of this IN minus form will be produced. And so when the ratio of the concentration of IN minus to the concentration of HIN is equal to 1/10, and that means 1/10 of our initial form, the acidic form of the indicator, was converted to the basic form. And so that's when we'll see that color change. Whereas if we start with a basic solution and we're titrating with an acidic solution, then the initial form is IN minus, and as we add more acid, more HIN will be produced. So when this ratio is 10/1, then that's when the color change will happen if we start with a basic solution. And so since the indicators are just weak acids, of course they have a Ka value associated with their equilibrium. And we can find the pH range of an indicator, which is just when the color change will occur, using the Henderson-Hasselbalch equation. So we have the pH will equal the pKa plus the log of the ratio of the concentration of the base to the acid. And we know that the color change happens when this ratio is 1/10 or 10/1, depending on which side we start from. So this tells us that the color change will happen when the pH is equal to the pKa of the indicator plus or minus 1. So for any indicator, we just take the Ka value of it, and then we take the negative log of that, and the pH range will be the pKa plus or minus 1. So if we start from a basic solution, then the color change will occur when the pH is equal to the pKa plus 1. Whereas if we start from an acidic solution, the color change will happen at pKa minus 1. So when we choose which indicator to use for a specific titration, we need to make sure that the pH at the equivalence point is inside the pH range of an indicator. Or else, if the equivalence point is too far from the pH range, then the indicator will change color too quick or too late, and so it's basically useless, because the whole point is to have the color change indicate when the equivalence point occurred. So that way we can measure how much titrant we added.